Okay, Nana. After completion of formation of cations, now I'll go for the formation of anions. How anions will be formed? How anions will be formed? It is relatively simple compared to the cation formation. Cation formation is the property of metals. Metals tend to lose electrons. Metals tend to lose electrons means they lose on losing electrons, they will form cations. Some metals are tending to get octet configuration as we predicted. Some metals during formation of cation getting the pseudo noble gas configuration. Some metals without getting anything, that means inert gas configuration or pseudo inert gas configuration, they are simply forming stable cations. But when come to the formation of anions, non-metals tend to form anions by taking electrons. Non-metals accept electrons, they take electrons. That is the property of non-metals. Highly electronegativity, small atomic size, high electron gain enthalpy, electron attachment enthalpy. I given one example, Nana. Straight away, first example you see chlorine here. And this symbol is nothing but called Lewis dot symbol here. Chlorine is the symbol of the element. If you see this one, 1s2, 2s2, 2p6, 3s2, 3p5, that is the electronic configuration. This is the outermost shell. So whatever I represent here, that is only I represent outermost shell, valence electrons. In 3s, 2 electrons are there. So that is a pair, electron pair. I written here. In a 3p, number 2, number 3, that means 2 electron pairs are there, I written here. That means electron pair, I'm showing like a dot. Electron, I'm showing like a dot. This is called Lewis dot symbol. Pair 2 electrons like this, 2 electrons, and this is single electron, I'm showing like this. So I will continue to write like this, Ranak. So that means until I complete Lewis theory, many times I will write the elements like this. That means these are called Lewis dot symbols. Okay. So if you see the electronic configuration, it is just short of 1 electron to get octet configuration. Short of 1 electron means if I provide 1 electron, otherwise chlorine takes accept 1 electron for somebody, and it will get immediately 8 electrons around it in valence shell. Valence shell means outermost electron. 1 electron is taken here. This is converted to 3s2, 3p6. It is stable electronic configuration because it's the accepting single electron. It is having negatively charged ion, 1 negative charge. So when you come to the chlorine, chlorine is the group 17 element that is called halogen. I given one example of halogen, but what about other halogens? And other halogens also I given here. Earlier I told you the ease of formation of cation is directly proportional to metallic nature. In this case also, the ease of formation of anion is directly proportional to non-metallic character. Best non-metal can form easiest anion. So fluorine is the best non-metal. That means fluorine forms easily F minus compared to the chlorine, compared to the bromine, compared to the iodine. So in this direction, non-metallic character increases. In this way, non-metallic character increases. Non-metallic character increases means the ease of formation of anion also increases. Electronegativity increases. So you see the arrow mark here. Here I written here the arrow mark. The arrow mark is showing upward direction. That means it is the bottom to top of the group. Bottom to top of the group. So ease of formation of anion increases. I written the reason also. Atomic size decrease, increase in electronegativity. Electron gain enthalpy is also plus 0.1 here. So less atom means the added electron can easily be held. And less atomic size means the added electron can easily be held. More electronegativity means the same thing. That means the added electron can easily be held. So F minus is the most easily formed anion. Cesium plus is the most easily formed cation among the periodic table elements. So I can say the best cation in the periodic table element atoms is cesium plus. The best anion is nothing but F minus. So the electrostatic attraction between cesium plus and F minus is the greatest. So that is the electrostatic attraction is greatest depends. You are calling that one as ionic bond now. So they form best ionic bond. Cesium plus and F minus form the best ionic bond. That ionic bond is taken as the 100% ionic bond. Taken as, okay. That is for your understanding. Okay, next I give a next element that is oxygen. Oxygen, you see 2s to 2p4 is the outermost electronic configuration. 2s one electron pair is there. 2p another electron pair is there. These two electron pairs I written as two dots here. Two dots here. These are two single electrons. You see I written single electrons like this. If you see the oxygen group 16 element, okay, oxygen is the group 16 element. It is short of two electrons. If it gets two electrons here like this, it will get noble gas configuration. So by some other source, somebody giving two electrons this oxygen, it takes it. And now you see it is getting octet configuration. I am clearly showing that one. 8 electrons around the oxygen valence shell number. Here also configuration wise also I am showing that one. It is nothing but neon configuration. Because it's taking two electrons, it gets two negative charges. So this is called oxide ion. You see, the nomenclature of ions is not directly equal to element name. The nomenclature of cation is directly equals to element name, but whereas in this case, it is not directly equals to, okay, Nana, it is not directly equals to element name. F minus, Cl minus, Br minus, I minus are called fluoride, chloride, bromide, iodide. You see IDE at the end. Okay. So you observe that word. And this is nothing but called oxide. Here also IDE is there. I told you this is chalcogems. Chalcogems means group 16 elements. Okay. What about the other elements of group 16? Other elements also I given oxygen, sulfur, selenium, tellurium. They also form divalent anions, bivalent anions. Halogens form monovalent anions and group 16 elements, chalcogens form divalent, bivalent anions. So it is called oxide sulfide. S2 minus is sulfide, Se2 minus, two negative charges, selenoid. Te2 minus is telluride. Other elements also there, Nano, but I'm not writing them. They don't form, that means the oxygen, sulfur, selenium, tellurium. Next element is also there, polonium, that is a metal. Actually, polonium is a metal, means metallic nature increases down the group. Now. Here also I avoided aster type, okay. Here I am just writing the stable divalent anions that can be studied, okay. Anyway, which is going to form easily this oxide ion, that means the divalent anion among the group 16 elements, which is easily formed oxide. Definitely small atomic size, more electronegativity, and these reasons are favorable for oxygen. But if you compare with the halogens, group 17 elements, they are just taking one electron. Taking one electron, adding one electron is very good. That means they liberate energy in that case. But these group 16 elements are taking two electrons. They are taking two electrons, means adding second electron is difficult. I already explained this one in terms of electron energetics, electron gain enthalpy. It's okay in the periodic table. So I can say halide ions are easily formed compared to these group 16 divalent or bivalent ions. That is very obvious point. Okay. Very well. Now one more point. That means I come to the pnictogens. That means group 15 elements, nitrogen family. You see nitrogen Lewis dot symbol you can see here. 2s2 2p3, 2s2 pair is there, that pair I'm showing here. 2p3 means all these are single electrons. You see, I'm showing the single electrons here. It is short of 3 electrons to get the stable electronic configuration. Getting 3 electrons is difficult, man. That means adding one electron, successive electrons is not easy. But it still exists. It's a very stable ion. Okay. So it is taking 3 electrons, means it gets 3 negative charges, and it gets 3 electrons are taken, 1 here, 2 here, like that. You got the octet configuration around the nitrogen. Okay. Electronic configuration wise also I showed you. And neon electronic configuration, it is getting octet. So far, I told everything, every example followed Lewis octet rule. There is no violation. Okay. But what about the other group 15 elements? Nitrogen, phosphorus, arsenic, antimony, bismuth is also there. But I'm not showing antimony and bismuth. I'm only showing the sure elements. So relatively stable elements. Nitride, here also you can see phosphide, arsenide. So these are the some most important ions of the periodic table. But if you see, so far I given group 17, group 16, group 15 most stable ions. All these are having single atom, only single atom. F minus, Cl minus, O2 minus, S2 minus. S2 minus means S2 negative charges. N3 minus, that means nitrogen 3 negative charge. All are having the single atoms. These are monoatomic anions. Monoatomic anions. All are having the stable electronic configuration. So that's all done. That means for the formation of anion, there is no much difficulty. A very small number of non-metals are there in the periodic table. I already covered all of them. All of them are covered there. Some other ions you will eventually get in further discussion. Right now, it's not necessary. Now, in the next point, after formation of ions, I'm coming to the point number 11. You already know what is ionic bond. Ionic bond is electrostatic force between cation, and that means cation, anion held together by electrostatic force of attraction. Electrostatic force of attraction means attraction between two opposite charged ions. That is nothing but called ionic bond. Ionic bond is not having any direction, any particular direction. That means it is not non-directional bond. Electrostatic attraction means attraction is there everywhere around the entire sphere. So it's not having any directional properties. Because it is not having any directional properties, that means it is having a different nature. Ionic bond is there, means the compound is called ionic compound. The compound is called ionic compounds. Ionic compound, best example is NaCl. I just given that example. NaCl consisting of Na plus and Cl minus. Now, this is cation and Cl minus. Both are held together by attractive forces. When NaCl, we don't call it as a molecule. No, we don't call it as molecule. Ionic compound, we will call it as formula unit. Formula unit. So, for example, CH4 is there. That is molecule. Okay. And its molar mass is called molecular mass. That is called molecular mass. For NaCl, that is called formula and formula unit mass. Molecular weight is there now. That molecular weight we will call it as formula unit mass. Okay. So anyway, you already know this one, but I written here as example number 1. You can easily get this point because it's a straightforward. Formation of sodium chloride example I taken here. You can see sodium electronic configuration 3s1. Lewis outermost shell only I have to show here. Lewis dot symbol. Chlorine you already know. Here instead of writing box representation I written 3px2, 3py2, 3py1 and 3s2. These are 3 electron pairs. These 3 electron pairs are written outermost shell only. Don't go for the core electrons, inner electrons. Here 3pZ1 means one single electron is there. It needs an electron. It wants to donate electron. If it gives electron, the remaining is noble gas configuration. If it takes electron, it gets the noble gas configuration. Both win and win situation. It loses electrons and become Na plus. It gains electron, becomes Cl minus. Everything you know, the outer shells are now having the 8 electrons. Both are getting octet. Na plus and Cl minus held together by electrostatic forces. But the strength of these electrostatic forces is measured in lattice enthalpy. That is again very serious discussion, lattice enthalpy. I'm not going to discuss lattice enthalpy. It is like electron gain enthalpy, ionization enthalpy, lattice enthalpy. Even I don't want to tell the definition right now. Lattice enthalpy will be detailedly discussed in thermodynamics. Now it is very difficult for a student to understand that lattice. If I discuss now, you immediately feel very difficult situation. You are in the difficult situation. Okay. So lattice enthalpy is a measure of strength of ionic bond, electrostatic attraction, okay, electrostatic forces. Later on, you'll get the complete description of the lattice enthalpy, right? And in a 12th class, solid state, one chapter is there, completely chapter dedicated to solids. In that solid, ionic solids also, their structures also detailedly discussed now. Now, at this point of time, I'm not discussing those structures, but I will simply say ionic compounds form three-dimensional structures in solid state. Solid is also called crystal now. Ionic compounds in crystalline state, that is nothing but solid state. Crystalline is the very sophisticated word for the solid, simple solid state, consisting of an orderly three-dimensional arrangement of cations and ions. Very beautiful order will be there. Sodium chloride crystal structure is called rock salt structure. And right now, I'm not giving any information regarding that. You will get that one in solid state of the class. Not now. Now, this is the one example I given. You are feeling very easy, I know that, because you learned this one many times in lower class also. And now, yesterday and today also, I already told you how cation is formed, how anion is formed, because it is straightforward. So, as a, for example, another example sake, I am giving calcium fluoride formation. You see, calcium electronic configuration 4s2 is there. These two electrons are written here now, like this. These two electrons are going to lose. That means calcium is going to lose these two electrons. By losing these two electrons, it gets a stable octet configuration. Calcium losing two electrons means calcium gets two positive charges. Here I written that one. So it is having organic configuration. It's stable. And one electron is taken by one fluorine atom, another electron is taken by another fluorine atom. Fluorine electronic configuration also I clearly written here. And fluorine taking this electron becomes octet. Here also fluorine taking this electron becomes octet with Fo minus. So one calcium 2 plus 2 Fo minus forms one formula unit. That formula unit is calcium fluoride CaF. So this is how you get the formation of ionic compounds. And yes, I am not worried about that, because you already definitely, this is, if I'm discussing, you feel this is really easy. Yes, it is not at all difficult. It is easy only. And 2-3 simple words, if you learn, I'll finish ionic bond formation. Ionic bond having the cations and anions, ionic bond is also called electrovalent bond. So paper setters will ask, what is electrovalency? Electrocovalency. Covalency is nothing but the ability to form covalent bond. If I am having covalency 3, I can form 3 covalent bonds. If I am having electrovalency 3, I am forming either cation having 3 positive charges or anion having 3 negative charges. Electrovalency is nothing but the charge present on the cation or anion directly. So ionic bond is definitely called as electrovalent bond. Electrovalence is directly equals to charge of its ion. I given some examples here. Anion, anion or cation, whatever it is, just directly take the charge to find the electrovalence ion. And one more last point, that is the point number 12. Last points in ionic compounds. Okay. I given some basic properties of ionic compounds. Anyway, you will get this one in the 12th class also. Ionic compounds are really hard, Nana. Their melting and boiling points are very, very high. Because ionic bond is the strongest bond known. It is stronger than the any covalent. Attraction, attraction between opposite charges. So ionic compounds will have really, for example, sodium chloride melting point is 803 degrees centigrade. Degrees centigrade now. More than 1000 kelvins. If you convert it to kelvins, around 1070, 1080 kelvins. Around. So that means it is having really high melting point just to melt the sodium chloride, NaCl. And why I'm telling NaCl? NaCl is a table salt. Every day you are consuming sodium chloride. Consuming more sodium chloride is dangerous. Hard and ionic compounds are hard and possess high melting and boiling point. That is one thing. Ionic compounds are soluble in polar solvents. So immediately, sir, what is this polar solvent, sir? I never heard the word polarity. Yes, I do agree that, but right now, polar solvent best example is water. You are every day seeing. Even now also you can just dissolve sodium chloride in water, it dissolves. So what is the polar solvent? What is the meaning of polarity? In the same chemical bonding, I will discuss now. That is entirely different. But ionic compounds are not soluble in the non-polar solvents. Non-polar solvents having no polarity. Benzene, CCl4, I given some examples here. So right now, even though you don't know what is polar, non-polar solvents, just to take it granted, later on you will get the clarity. And another property, conducting them. Ionic compounds are good conductors in fused state and dissolved in water. What is the meaning of fused state? I just told you now. You take sodium chloride solid, readily there. Okay. Solid sodium chloride does not conduct any electricity. No, it doesn't conduct any electricity. Only you after melting that means solid sodium chloride having Na plus Cl minus ions in a fixed position. They don't move. To have the conductivity, ions has to move. So ions carry the electricity through them. So the movement of ions is only possible when you melt sodium chloride. That is called fused state. Fused state means without adding in water, you are just melting the sodium chloride. When in the molten sodium chloride in fused state, ions are readily flow and they carry electricity. That is, ionic compounds are conductors in fused state, not in the crystalline state, solid state. But when dissolved in water, completely ions break up. That means Na plus Cl minus become free. They are readily conduct electricity. That's why this property is very important. You can straight to understand that property also. This one I already told you, ionic bonds are non-directional. Ionic bonds are non-directional. Only covalent compounds show isomerism. Isomerism means same molecular formula, different structures. The structure thing is only for covalent compounds, not for ionic compounds. Okay. Crystal structures are different now. That is a combination of so many ions in one three-dimensional array. That is completely different. Okay. So there is no isomerism for the ionic compound. No isomerism. Isomerism is the property of covalent compounds. Isomerism means same formula, different structures. Later on, you will get that one in detail. So that is the ionic bond. That is the Lewis concept. And that just now I explained, I finished the ionic bond. Now point number 13. So I'm continuously running the points here from the first chapter onwards. I suggest please write the notes immediately. And every day, don't keep any lagging in the notes. You writing the notes is the first step to study now. Okay. So covalent bond explanation by Lewis now. Still I'm discussing Lewis theory. Only after completion of Lewis theory, I will go to the other theories. Ionic compound discussion is over now. That is complete. Now covalent bond, how a covalent bond is formed by non-metallic elements. Similarly, electronegative elements. Ionic bond is formed between electropositive metal, electronegative non-metal. Ionic bond is formed between atoms of elements which are having large difference in electronegativities. Sodium chloride, sodium electronegativity 0.9, chlorine electronegativity 3.0, large differences there. Covalent bond is formed between non-metallic elements, generally. Non-metallic elements means elements having the same electronegativity, similar electronegativity. Electronegative difference must be very less. That is the first prerequisite condition to form a covalent bond. But the covalent bond formation is more complicated compared to the ionic bond formation. That's why so many theories are there. Right now, I'm going to discuss Lewis theory. Afterwards, I will come to the valency bond theory proposed by Linus Pauling, student of Lewis. After that, as the highest level, molecular orbital theory also I will discuss now. Molecular orbital theory to some extent I will discuss. Okay, that is their only syllabus. Now, what Lewis is telling? Lewis theory is the same now. That means getting octet configuration is the ultimate aim for anything. In case of metal non-metal combination, metal loses electron, non-metal gains electron, so that both get the stable electronic configuration, octet. But when come to the bond between two similarly electronegative atoms, that means two similar atoms, two same non-metals, they get the stable octet configuration by sharing of electrons. Sharing of electrons leads to the covalent bond. In case of ionic bond, there is a complete transfer of electron. Electron is completely transferred from sodium to chlorine. Sodium lost electron, forming Na+. Chlorine gains electron, forming Cl-. Then Na plus Cl- pulled together and forming electrovalent bond or ionic bond. But in this case, there is no formation of cation and anion, nothing. But two elements, two atoms of elements, a same element or different element, but non-metals. Similarly, electronegative elements share electron pair between them so that both get benefited, both get stable octet configuration. So they form a covalent bond. If they share one electron pair, one covalent bond. If they share two electron pairs, two covalent bonds. Two covalent bonds formed between two atoms is called double bond. If three electron pairs shared between them, three covalent bonds. Three covalent bonds formed between two atoms is triple bond. Now, I given one example. Straight away, I'm taking the most famous example. This is the easiest to understand. Lewis dot symbol for hydrogen, its electronic configuration 1s1. It is just a short of one electron to get helium, very stable duplet, helium configuration. Another hydrogen atom I take it. It is also same fate. That means it is also, so this hydrogen wants one electron to get a duplet. This hydrogen also want one electron to get a duplet. Now what happens? These are same electronegative, same element, atoms of same element. These two electrons are shared between these two atoms. So I have shown the sharing of this one. Okay. Why I round it off here? Because this hydrogen getting now duplet. So these two electrons now after sharing, Before sharing, this electron belongs to this atom. This electron belongs to this atom. After sharing, these two electrons belongs to both the atoms. So this hydrogen getting 2 electron duplet. This hydrogen also getting 2 electron duplet. Both are stabilized. Hydrogen molecule is very stable compared to the hydrogen atoms. So duplet by sharing of an electron pair. The shared electron pair is nothing but called bond pair now. Now onwards, you have to be really memorize these words. Not very easy words. Repeatedly, you will get this bond pair and lone pair. Now, right now, bond pair. Bond pair is nothing but the shared electron pair is called bond pair. And instead of writing this like this, Nana, so writing this every time is difficult. Na? This is called Lewis dot symbol, Lewis dot structure. That writing like this is called Lewis dot structure. Nana. Okay. Writing like this is very easy. Nana. You see, this bond pair of electrons replaced by a dash. That is very famous. Now we are following that one. Right? So that is that means there is a little confusion. Who introduced this dash for this one? Lewis and Cosell, I told you, both worked independently, not together. And somebody say Cosell introduced this representation. Somebody say Lewis, I am not having clarity. Okay, I don't want to go into that unnecessary argument. Okay, anyway, this is very comfortable, very comfortable than this. Okay. Because it is easy now writing like this. Writing instead of writing every time like this is difficult now. So for example, I want to write a chemical reaction H2 plus Cl2 like this. And writing like this is very easy to me. And writing this like this is very difficult now. So now I have to write everything. So many electrons I have tried. Okay. So somehow it is very convenient. And the reason here I written single covalent bond. What is the meaning of that? Sharing of one electron pair, only one electron pair leading to the single bond, single covalent bond. So now come to the next example. Next example is nothing but fluorine atoms I take it. See, this is the valency shell. Okay, na? It is having pair of electron. It is not participating in a bond. The electron pair which is not participating in a bond is called lone pair. Lone pair. Okay, number. This electron pair is also not participating in a bond. That is lone pair. This is also not participating. Lone pair. So 3 lone pairs are there. 1 single electron is there. It is just short of 1 electron to get the noble gas configuration, octet configuration. Similar fluorine atom. Both are same. So it is also just short of 1 electron. So these 2 electrons are shared between both the fluorine atoms. So this is shared electron pair. Once shared means these 2 electrons belongs to both fluorine atoms, this atom and this atom. Now you see, including these 2 electrons, now fluorine is having 8 electrons around it in its valence shell. This fluorine is also having 8 electrons around it. So both are getting the octet configuration. Both the fluorine atoms are getting octet configuration. The shared electron pair is nothing but called bond pair, BP. Every time writing bond pair is difficult for me. I will write BP, small letters. Okay. Right. Don't confuse with the boiling point. Generally, boiling point is written capital letters. Okay. Don't confuse with the blood pressure. BP is also known as blood pressure. Okay. Right. Don't confuse. Okay. There is no word blood pressure in chemistry, that is biology. Okay. Now, these unshared electron pairs means the electron pairs which are not participating in bond. Nothing but lone pairs. Lone pairs are represented as LP. LP means lone pairs. So that is fluorine atom. So instead of this one, I can write a dash. I can put a dash. Everything else I written now. That means lone pairs I'm still showing that. Some paper setter ask the question also. He says, how many lone pairs are there in that molecule? Okay, how many bond pairs are there? How many lone pairs are there? That kind of questions you will get. You just started the subject, later on, I will give the some information how to calculate load pairs, bond pairs, everything I will provide. Don't worry about that. We just started the journey to learn the covalent bond. It is a really long journey. No? It's a big one. It's a really lot of things we have to learn. And sharing of one electron pair between two fluorine atoms resulting the single covalent. Okay, number. That is the formation of F2 molecule. So here hydrogen getting duplet, here fluorine is getting octet. Very well. Now come to the next example. Let me discuss some examples. Examples are important here. So let me discuss some examples. Okay. Now come to the oxygen atoms. Now, two oxygen atoms I taken. I written the electronic configuration here. This is the valence shell. Two electrons, lone pair. In this orbital, two electron, lone pair, not participating in bond. These single electrons are written like this. It is short of two electrons to get the octet configuration. This is also another oxygen atom. Same, everything is same. Two lone pairs and two singles. Now what happens? These two electrons are shared between two atoms. These two electrons also share it because it needs two electrons to get octet now. That's why this one shared, this one shared. Because of sharing of this electron pair, you will get one covalent bond. Because of sharing of this electron pair, you will get another covalent. So you are going to get two covalent bonds. So two electron pairs are shared, two covalent bonds. That is called double bond. Now I clearly written here. So you see, both oxygen atoms are sharing two electron pairs. So it will get the double bond. So two dashed lines. So during this process, both the atoms are getting octet configuration. You can see 2, 2, and these 4, 8 electron, 2, 2, and these 4. These are the lone pair of electron. These are the bond pair of electron. Two bond pairs are there and 4 lone pairs are there. Right now, I'm not doing that thing, okay? Counting bond pairs, not. Right now, you have to learn the subject, the concept first. Later on, come to that applications, okay? So sharing of two electron pairs, formation of two covalent bonds between the oxygen atom, that is nothing but called double bond. Okay, this is nothing but oxygen formation, O2 molecule, explained by Lewis concept. Now, I'm discussing Lewis concept now. See, so observe that these two bonds are two covalent bonds now. Two covalent bonds according to Lewis theory. Now come to the next example now, formation of nitrogen molecule. I'm explaining Lewis concept now. So many different examples I taken. I want you to learn how a single covalent bond is formed by octet and by duplet. How a two covalent, double covalent bond is formed between two atoms. How a triple covalent bond is formed. Now I'm explaining the formation of triple covalent bond. Three covalent bonds, okay? Nitrogen outermost electronic configuration. Inner electrons I don't take. Lone pair here, single electron, single electron, single electron. Directly called this is lone pair. That means it is not participating in bond formation. It is short of 3 electron to get octet. Another nitrogen atom also same problem. So these electrons are shared. So this sharing of one electron pair gives one covalent bond. Second electron pair gives another covalent bond. Third electron pair gives another covalent bond. So you'll get the 3 covalent bonds between 3 nitrogen atoms. Okay, Nana? So once you got the 3 electron pair shared, you will get the octet configuration. You can clearly see that. Both the nitrogens now satisfied, they are getting, both nitrogen atoms are getting octet. This one are shown like a 3 dashed lines. Okay, N lone pair and this triple bond here, nitrogen lone pair. So that is never, I told you, do not apply valency bond concepts to Lewis concept. Don't get confused there. A paper set that much clever questioning is not there nowadays. Okay. 3 covalent bonds between nitrogen atoms. 3 covalent bonds between nitrogen atom. See, 3 covalent bond. That is nothing but called triple. So with this, I definitely explained. I feel that I definitely explained the Lewis concept. Now, sharing of electron pair leads to formation of covalent bond. 2 electron pair share double bond. 3 electron pair share triple bond. But once you understand the basics of Lewis concept, now how to write Lewis dot structures? These are not structures, mean don't confuse with the real structures now. Every molecule will have a real structure. I'm not talking about that. Lewis concept unable to predict the geometries. Structures means don't go to the geometries. That is a drawback of Lewis concept. It does not predict the geometries of the compounds, molecular compounds. Molecular compounds means covalent compounds. Okay. For example, methane is there. Methane geometry is a tetrahedral. Generally, colloquially, what is the structure of methane? Tetrahedral. Lewis structure is different. Lewis structure is nothing but around the central atom, how many bond pairs are there, how many lone pairs are there. Terminal atoms, how many bond pairs are there, lone pairs are there. Every atom is getting octet or not. That's what it shows, Lewis dot structure. How to write it? Directly you can write like this. That means you can directly write atoms with electronic configuration, share the electrons. This is called Lewis dot structure. This is itself. I directly return with this explanation with the bond. Share this electron pair shared, this electron pair. You can also do that. Directly you can write that. But sometimes if you are in a hurry, you can alternatively write the Lewis dot structure. I taken one beautiful example, NF3. I am just asking, write this kind of structure to NF3. Sir, I will take nitrogen. Here, just for your consideration, I written nitrogen electronic configuration, fluorine electronic configuration. You can do like this. Nitrogen having lone pair, these single electrons are there, sir. Fluorine, each fluorine is having, already shown to you. And these 2 electrons share. You will get a shared electron. Like that, like this, you can write now. It is very easy actually. Amma, be careful, Rana. I'm just telling so many different ways of writing. Yes, you got the Lewis dot symbol. You see here I written now. Directly you can write like that. No, but no objection. But alternatively also you can write. Okay, another procedure is also there. What is the best procedure? You nobody say. Whatever the procedure you like, you can follow that. I'm not bombarding with different things. Simple things here. If it is one procedure to write the Lewis dot structure like this, that means how bonds are, how electron pairs are arranged around the atoms. NF3 means first of all you have to find total number of valence electrons. It is having 5 valence electrons, nitrogen outermost. Fluorine is having 7 valence electrons. Total number of valence electrons means 5, 1 nitrogen, 3 fluorines, 7 multiplied by 3, 26. So 26 valence electrons are there. That means 26 electrons are there in the Lewis dot structure. You divide with 2, you will get number of pairs. Everything, bond pairs, lone pairs, everything, all kinds of pairs. I'm not specifying bond pairs and lone pairs. I'm simply writing number of electron pairs. 2 electrons, 1 pair, so 26 by 2, 13 electron pairs are there. Remember, everybody should get octet configuration. Hydrogen, if hydrogen is there, it should get duplet configuration. So how to write this one on 13 electron pairs? So nitrogen, you see, nitrogen is having 3 fluorine atoms. Okay, na? So every nitrogen fluorine is shared by 1 electron. So I'm just telling alternative procedure to write the Lewis dot structure. And this is definitely sharing must be there. Na? And nitrogen on lone pair is there. So I'm writing this one. You say nitrogen got octet configuration. Fluorine electronic configuration, one single electron, that means using the single electron is shared with nitrogen. Every fluorine is having 3 lone pairs. You see the configuration, already you know the configuration, 2s2, 2px2, 2py2, 2pz1. 3 lone pairs are there on fluorine atom. Using this electron, it is forming bond with the nitrogen. So every fluorine is getting octet configuration. That's all. So no complication is there. But in this one, that means if you, so for this carbon monoxide, I'm going to write Lewis dot structure. It's a really complicated, it's a tough example. What complication is there here? I'm writing carbon electronic configuration. So 1s2, no, you see, I'm not using, I just calculate total valence electrons, number of electron pairs just to count. In the previous example also, I told 13 electron pairs. You can count 13 electron pairs. Around nitrogen 4 are there, and each fluorine is having 3. Okay, 3, 3, 3. 3 times 3, 9, plus 4, 13. 13 electron pairs. Okay, 13 electron pairs mean 26 electrons. That's what I'm telling. Only to find that one, okay, this is the electronic configuration of carbon, 2s2, 2px1, 2py1, 2pz0. It is empty orbital. Be careful. One empty orbital is there here. Nothing is there. Oxygen electronic configuration, you know, 2s2, 2px2, 2py1, 2pz2. How many valence electrons are there? 4. Here, 6 valence electrons are there. So total number of valence electron, 1 carbon atom, 1 oxygen atom, 4 plus 6 is 10. Number of electron pairs, 5. I am not following the earlier procedure, this procedure to write the Lewis formula. I am just following the basic thing. What I explained in the fluorine, oxygen, nitrogen, I explained the same procedure I have tried. I feel that is very easy and comfortable. This lone pair I written here now. Please see. Carbon is having 1 lone pair now. So that I written here. These 2 single electrons are written here. What about the oxygen? Oxygen 2 lone pairs are there. 2 single electrons are there. Listen carefully now. Now what happens? Carbon need how many electrons? It is having only 4 electrons. It needs 4 electrons to get octet. Oxygen having 6 electrons. It needs 2 electrons to get octet. So these 2 electrons, single electrons are shared. You will get 1 covalent bond. These 2 single electrons shared, you will get another covalent bond. You see, I written this one. So carbon, 1 lone pair is there. That is inherently there in the electronic configuration itself. Oxygen 2 lone pairs are there. Be careful. This single electron shared here. 1 covalent bond. This single electron shared here, another covalent bond. But there is a problem with this structure. There is a problem. What is the problem? Now oxygen, you see, this is the oxygen. These 4 electrons now belong to both carbon and oxygen. Now, oxygen getting octet. 4, 6, 8. But carbon is not getting octet. 4 plus 2, 6 only. Having the 2 electrons is duplet. Having the 6 electron is octet. Having the 8 electrons is octet. Having the 6 electron is called sextet. So carbon is having only 6 electrons. Louis does not agree. What is this? You are violating my theory. For carbon, second period elements, it is not allowed. Carbon should get 8 electrons. Sir, how, sir? So you have to find some way. Carbon should get 8 electrons, octet. I'm not seeing any possibility here. So how this single electron shared, this single electron shared, everything is in perfect condition, but the carbon is having only 6 electrons in. Now, this is important here. This is so important here because this is important. Because carbon need octet, oxygen donate this lone pair. Lone pair friends actually doesn't participate in any bond. But in this case, what happens? Oxygen donates lone pair. That means this pair of electron. Now it is not called as lone pair. Into the empty orbital of carbon. Here empty orbital is there, 2 p Into this empty orbital of carbon, it donates electron pair. After donating, these 2 electrons are shared between both the atoms. See, he written to get octet for both. Oxygen donates 1 electron pair to carbon. This is the empty orbital. Here clearly, again I written carbon electronic configuration. Empty orbital to accept electron pair from oxygen. Here I am showing that one. So this is nothing but electron pair is donated here. That means to carbon. And this Nana, everybody. This electron pair is donated by oxygen to carbon. Oxygen is donating, carbon is accepting. Once donated, these 2 electrons shared between 2 atoms. The bond, this bond is covalent bond. This is covalent bond. 1 electron is coming from carbon. 1 electron is coming from oxygen. Okay. This is also 1 electron is coming from oxygen. 1 electron is coming from carbon. Covalent bond. Covalent bond. But here 2 electrons, both the electrons are coming from oxygen. That bond is called day-2 bond. Day-2 bond. Somebody is donating. That is nothing but called coordinate covalent bond. Coordinate covalent bond. So here I written that one. That means you see now, once these 2 electrons are coming here, now this carbon is having octet configuration. 6 here, 2 here. Oxygen is also having octet configuration. So both are getting the octet configuration. Here I written to get octet for both, oxygen donates 1 electron pair to carbon, leads to formation of day-2 bond. That is nothing but called coordinate covalent bond. What a beautiful analysis by Lewis. This is not my theory. No. This is Lewis' theory. Explained carbon monoxide structure so successful. Nice explanation. Very good explanation. So with that day-2 bond, okay, sir, you are showing the single covalent bond like dash line. How day-2 bond is shown? Oxygen is the donor, carbon is the acceptor. So day-2 bond is shown like this. That means it is the arrow mark like this, showing that it is donor, it is acceptor. Okay, that means the 2 electrons are required for bond formation. Both the electrons required for bond formation is donated by oxygen. I written there. Both electrons are required for bonding, donated by oxygen and shared between carbon and oxygen. Every information I written on. Right. So now you see, so this is the carbon monoxide structure now. That is the Lewis structure, okay, of carbon monoxide. Very well. But one more thing you have to learn. So instead of writing day-2 bond, listen to my words carefully. I showed the day-2 bond like this now. You can also write a simple covalent bond like this. Now I'm not showing the day-2 bond. But if you are not showing the day-2 bond, this is very, very important information. Throughout 2 years, you will see this one repeatedly. And if you don't learn well now, you feel very difficult later on. So I'm taking really a lot of time. Okay. So this day-2 bond, instead of writing that, I simply write a line here. Then what happens? Oxygen donating 2 electrons. Listen to my words now. Donating 2 electrons. Now these electrons shared between carbon and oxygen, but Oxygen, in fact, not donating 2 electrons. These 2 electrons, 1 electron still there with oxygen only. Carbon getting 1 electron extra from oxygen. So because oxygen losing 1 electron, you assume like that. That means out of the 2 electrons, 1 electron is close to the oxygen, 1 electron is close to carbon. Oxygen losing 1 electron, carbon gaining 1 electron. You have to assume like that. So carbon is getting 1 electron extra, it gets negative charge. Oxygen losing 1 electron, be careful, it is donating 2 electrons. Don't think that both the 2 electrons are completely gone for carbon. No. Out of the 2 electron, you assume that 1 electron is taken by carbon. Still, oxygen is having holding 1 electron. So, oxygen just lost 1 electron, gets 1 positive charge. Carbon is getting 1 electron extra, gets 1 negative charge. So, whenever you want to write this structure like this structure, you have to show the charges. Now you are showing the 3 covalent bonds. So you are showing 3 covalent bonds, friends. You have to show clearly positive charge and negative charge. That's why so many times in organic chemistry also, I will tell many times, oxygen forming 3 bonds, it is having positive charge. Like that. So this is the other representation of carbon monoxide. How you represent? Sir, here charges are there now, sir. What is this compound? It is still covalent compound, molecular compound. The positive charge is cancelled by negative charge. The molecule is neutral. That is neutral, cancels each other. Carbon monoxide is a neutral species. Definitely neutral species. Okay, Nana? So, but here, quite a drama is there. Listen. No, I'm not complicating the subject now. This is a nice flow of the subject. Okay. It's a very good flow of the subject. Okay. So these charges present on the carbon and oxygen are nothing but called formal charges. Those are called formal charges. Again, for formal charges. Instead of doing this entire thing, day-to bond and you getting the positive charge, negative charge and positive charge, instead of doing this entire analysis, in any molecule, my words are important. Here, I systematically, conceptually, I explained how charges are there on carbon and oxygen. Those are called formal charges. Carbon is having -1 charge, oxygen is having +1 charge. Instead of this, you can directly calculate formal charge in any molecule on a particular atom. Formal charge is there on an atom, on carbon atom, on oxygen atom. Okay, on atom. That formal charge, how much charge is there on that atom, you can directly calculate from a formula. That is the formula I am giving here. Here one formula I am giving. Formula means it's not difficult formula. This formula is just taken from my analysis only. That means I discussed in my analysis. From that analysis only, this formula is designed. That means the formula is already derived in doing my analysis itself. Formal charge and atom in Lewis structure, FC is a formal charge. Lewis structure means, just now we are discussing Lewis structures. First number of valence electrons present are carbon means 4 valence electrons. Oxygen means 6 valence electrons. Very simplest possible formula. I made it very simple. Minus number of unshared electrons. Unshared electron means electrons which are not participating in bond. Number of unshared electrons. Be careful, it is not pair. Unshared directly electrons. Minus number of bonds that atom is formed. Now come to the carbon monoxide. So this is the carbon monoxide structure I written like this. I don't know the charges, okay? I'm going to calculate formal charge on the carbon using this formula. Formal charge on carbon, valence electrons 4, number of unshared electrons 2, number of bonds it is forming. You see? Say What a beautiful theory, Lewis theory. I told you now, don't underestimate Lewis theory. Okay. So the formal charge in oxygen is nothing but valence electrons 6, unshared electrons 2, number of bonds forming 6 minus 5 plus 1. You will get it. So that means you learned now today. So how to write the Lewis structure in a simplest possible way. Don't take unnecessary things from unnecessary books. Okay. So the simplest possible way. And once you got the Lewis structure, you got the how a day-2 bond is formed, coordinate covalent bond is formed, covalent bond, coordinate covalent bond. Both you got today. And how to find the formal charges on atom in a molecule. Finding formal charge is really important. Nana. They decide so many things. Okay. If for a single molecule, my words are important. The last conclusion statement, and in the next class, the opening statement. For a molecule, if there are more than one possible Lewis structures, sometimes for a molecule, I can write 2 Lewis structures, 3 possible Lewis structures, 4 possible Lewis structures. I can write. The structure with the lowest formal charges is the most stable one. The structure with the lowest formal charges is the most stable one. So formal charge is the guide to write a proper Lewis structure. To find a Lewis structure written by you is correct or not, just to calculate formal charges. You experiment with Lewis structures and calculate formal. You write different Lewis structure for same molecule, calculate formal charges, select one Lewis structure with the lowest formal charge. That will be your answer. Okay, Nanda.